Imagine waiting like 18 hours to find out if you're actually going to be a parent. You've just gone through this incredibly grueling, physically exhausting process of an egg retrieval.
Right, which takes a massive toll on the body.
Yeah, it really does. And then in the embryology lab, the sperm and the egg, which, by the way, the literature always refers to as an oocyte, so we're just going to stick with oocyte today, they are finally combined.
And then the waiting begins.
Exactly. You go home, you try to sleep, maybe everyone breathes this cautious sigh of relief. But then 18 hours later, the embryologist slides your dish under the microscope, expecting to see, the spark of life. And instead, there's just nothing.
Just complete stillness.
Complete stillness. And today, for our deep dive, we are figuring out why that happens.
Yeah, that moment is... it's one of the most devastating scenarios in reproductive medicine. Embryologists call it a 0 PN state, which basically means total fertilization failure or TFF.
TFF.
And you're right, it's a complete standstill. But the lab doesn't just, throw its hands up and say, well, it didn't work. That exact moment is where the real detective work actually begins.
And that is our mission for you today. We are taking a massive stack of medical journals, lab manuals, embryology guidelines, and we're going on a forensic investigation. Because finding out what caused that standstill, it directly informs the clinical strategy to help you build a family in your next cycle.
It's all about figuring out the next steps.
Right. And to figure this out, experts use this core critical thinking framework. They call it the interpretation mindset.
Yeah, so the interpretation mindset is... it's basically a 4-part mental checklist. When an embryologist looks at that failed dish, they ask 4 sequential questions like what happened, why did it happen, is this expected based on the patient's history, and most importantly, what do we change for the next cycle?
I love that framework. It turns a tragedy into an actionable puzzle. So, to solve this mystery of TFF, to figure out why we ended up with 0 fertilization, we first kind of have to understand what the embryologist is actually looking for at the scene of the crime. So put us in the lab at that 16 to 18-hour mark.
Okay, so that specific time window is where absolutely everything hinges. At 16 to 18 hours post-insemination, the embryologist is looking for, well, the gold standard of success. In the charts, this is designated as 2PN, meaning 2 pronuclei.
2 pronuclei, got it.
Visually, they want to see 2 distinct spherical structures right in the center of the cell. One pronucleus contains the genetic material from the sperm, and the other one has the genetic material from the oocyte.
And they're also looking for 2 polar bodies on the outside of the cell, right?
They are, yeah. The polar bodies are essentially these little packets of discarded genetic material. Seeing them confirms that the oocyte has successfully resumed and completed its meiotic division.
Like it threw out the extra chromosomes it didn't need?
Exactly. But they don't just stop at counting those pronuclei. They also look inside them at structures called MPBs.
Right. I noticed that in the lab manuals. What exactly are those? Like, why does an embryologist care about them at 18 hours?
So NPB stands for nucleolar precursor body. Think of them as, like, the tiny organizational hubs inside the pronuclei. The embryologist wants to see these NPBs align perfectly at the exact junction where the male and female pronuclei touch.
Oh, so they have to line up.
Yeah, that alignment shows that the genetic material is preparing to merge smoothly. If those NPBs are just, scattered all over the place, or if they're wildly different sizes, it serves as a major red flag for chromosomal issues downstream.
So 2PN with beautifully aligned NPBs, that's the perfect normal state.
It's the dream, yeah.
But unfortunately, biology is messy, right? You don't always get 2PN. We're focusing on 0PN today, but what else pops up on that 18-hour check?
Oh, the lab sees all sorts of strange variations. Sometimes they see 3PN or even more. That usually indicates polyspermy.
Meaning a multiple sperm got in?
Exactly. Multiple sperm managed to breach the oocyte's defenses, leading to this disastrous overload of DNA. Other times they see 1PN, which often indicates parthenogenesis.
Wait, hold up. Parthenogenesis, you mean the oocyte just activates itself without any sperm DNA participating at all?
Yeah.
How does a cell just, glitch like that?
It is a totally fascinating biological glitch. Sometimes the oocyte experiences a spontaneous leak of calcium internally, or even just temperature changes in the lab can trigger a shock response.
Wow.
So the cell gets tricked into thinking a sperm has entered, and it wakes up and starts dividing based solely on its own half set of chromosomes. It's essentially a false start.
That is wild. The machinery just starts running with no one at the wheel. But okay, let's get to our main culprit today. 0PN, 0 pronuclei. You might assume 0PN just means the sperm got lost and never made it inside the oocyte. But the literature talks heavily about a phenomenon called silent fertilization.
Oh, Silent fertilization is incredibly frustrating for the lab. This describes a situation where the sperm successfully enters the oocyte. Sometimes the embryologist literally bypassed the shell and injected the sperm directly into the cell themselves using a microscopic needle, but absolutely nothing happens.
Nothing at all.
Nothing. The sperm head fails to decondense. Its chromatin, the tightly packed DNA, it just stays locked up in a tight little ball.
I was trying to visualize this while reading, and the best way I can think of it is like a critical delivery. Imagine you order this life-saving package. The delivery driver arrives and successfully drops the box just inside your front door.
Okay, I like this.
So physically, the package is in the house, but the recipient inside never actually walks over, cuts the tape, and opens the box. The contents are totally useless. The delivery happened, but the activation didn't.
That captures the mechanical failure perfectly. The package sits in the hallway, completely ignored. So this 0p state, it forces the lab to pivot immediately to the interpretation mindset. We know it's failed activation.
Right, so the next step is the why. Like, is the delivery driver incapable of opening the box, or is the recipient incapable of reading the instructions?
Exactly the question.
Yeah.
We have to interrogate our two prime suspects. So let's start with prime suspect number 1, the sperm's hidden machinery.
For the longest time, I think a lot of people just thought of sperm as, like, a tiny taxi cab for DNA. Like, it just swims there and drops off the payload.
A lot of people still think that.
But it is so much more than that, right? The sperm actually carries the match that lights the fire of life.
It absolutely does. The sperm is this incredibly complex delivery mechanism. And that match you're talking about is a highly specific protein factor called PLC-zeta.
Let's slow down here because the sources throw a ton of alphabet soup at this process.
Yeah.
PLC-zeta, PIP2, IP3. Break down how this spark actually works for us.
Okay, let's think of PLC-zeta as a pair of molecular scissors. When the sperm breaches the oocyte, it unpacks these scissors. The scissors float around and find a specific fat molecule in the oocyte's membrane called PIP2. The PLC-zeta scissors snip that PIP2 molecule right in half, and one of those halves is a new molecule called IP3.
Okay, got it. So the scissors cut the fat, and we get IP3. What does IP3 do?
IP3 acts like a master key. Deep inside the oocyte, there's this massive storage tank called the endoplasmic reticulum. It is packed to the brim with calcium.
Wow.
Yeah, so IP3 floats over to that storage tank, inserts itself into the receptor locks, and forces the doors wide open. This releases massive rhythmic waves of intracellular calcium.
The calcium oscillations. I saw this phrase everywhere in the reading.
Yes, those rhythmic spikes of calcium flooding the cell, they are the universal trigger for oocyte activation.
But why calcium? Like, what is a wave of calcium actually doing to the cell to wake it up?
Think of an unfertilized oocyte as a machine where all the gears are intentionally jammed. It's paused in the state of suspended animation, waiting for fertilization. The calcium waves activate specific enzymes that literally eat away the proteins jamming those gears.
Oh.
By degrading the proteins that were holding the cell cycle hostage, the calcium allows the meiotic gears to turn again. The cell wakes up, throws out that second polar body, and begins to form pronuclei. Without the calcium waves, the gears just stay jammed forever.
So if the sperm is missing those PLC-zeta scissors, the key is never made, the calcium never floods, the gears stay jammed, and you get 0pn.
Exactly.
But PLC-zeta isn't the only piece of heavy machinery the sperm brings. We definitely have to talk about the centriole.
Oh, the centriole. This highlights such a bizarre quirk of human biology. As human oocytes mature, they intentionally destroy their own microtubule organizing centers. They completely throw away the cellular machinery required to organize cell division.
Yeah, wait, so the egg deliberately makes itself incapable of dividing? It relies entirely on the sperm to bring the construction equipment.
100%. The sperm has to deliver a functional centriole. The centriole is basically the cellular architect. Once the pronuclei form, they need to physically move toward each other to merge. The centriole builds the microtubule bridges. Think of them as structural ropes, or like a winch system, that physically drag the male and female pronuclei into the center of the cell. If the sperm centriole is broken, the pronuclei might form, but they can't migrate. They just stay stuck on opposite edges of the cell, and fertilization fails.
That is fascinating. And the sources highlight specific conditions where we know the sperm's machinery is fundamentally broken. They talk about this rare morphological disorder called globozoospermia.
Yeah, globozoospermia is the classic structural failure. Under a microscope, you can spot it immediately. Instead of the normal, sleek oval shape, these sperm have a completely round head.
Just totally round.
Totally round. They lack an acrosome, which is the cap normally used to chemically burn through the oocyte's outer shell.
But even if we bypass the shell for them, they still fail, right?
They do, and that's the critical insight for 0PN. Studies show that globulospermic sperm, both type I and type II, are severely deficient in, or completely lack, that crucial PLC zeta protein.
So they literally don't have the scissors.
Exactly. You can inject them straight into the center of the oocyte, and the calcium tank will never open.
Okay, I have to push back here, though. Because globospermia is obvious, right? An embryologist sees a round head and knows there's a problem. But what if a man goes in for a standard semen analysis, and everything comes back perfect? The count is in the tens of millions, the motility is fantastic, the sperm look like Olympic swimmers under the microscope. Could that perfectly normal-looking sperm still be the culprit for TFF?
Absolutely, and this is a major point of frustration for patients. A standard semen analysis only looks at the macro level, how many, how fast, and what shape. It tells us absolutely nothing about the molecular payload hidden inside the sperm head.
So you can have, like, a Michael Phelps Olympic swimmer, but the cargo it's carrying is totally shattered.
Precisely. A sperm can swim perfectly, but completely lack PLC zeta. Or, perhaps more commonly, can have massive levels of DNA fragmentation.
Oh, interesting.
Yeah, if the genetic material is highly fragmented, which, by the way, can happen due to oxidative stress, smoking, or a varicocele, the sperm physically enters the oocyte, but its chromatin is too tangled and broken to decondense. The manual is completely shredded. This is why standard semen analysis is a notoriously poor predictor of actual fertilizing potential on a molecular level.
Man, that is a tough pill to swallow for patients who are told the male factor is totally cleared. So, okay, we've established the sperm can be holding a broken match, but what if we know the match is perfect? What if we use, say, donor sperm with proven fertility, we inject it, and it still fails? That means the problem has to be the kindling.
That logical pivot brings us straight to prime suspect number 2, the oocyte's internal environment. Because fertilization is a two-way street. Even if the sperm delivers the absolute perfect amount of PLC zeta and a pristine centriole, it just doesn't matter if the oocyte's internal machinery is fundamentally broken.
Right. And a massive theme in the literature when discussing the oocyte is the concept of maturation asynchrony, the difference between nuclear maturity and cytoplasmic maturity.
This distinction is everything. When an embryologist looks at an oocyte before injecting it, they check to see if it's at the M2 stage metaphase 2.
The sources mention M1 and M2, so M1 is immature, right?
Yes. In the M1 stage, the nucleus hasn't finished its prep work. Once it transitions to M2, it extrudes that first polar body. Seeing that polar body tells the embryologist that the nucleus is mature. The front office is open for business and has the correct half set of chromosomes ready to pair with the sperm. But nuclear maturity does not guarantee cytoplasmic maturity.
Okay, so the DNA is ready, but the rest of the cell isn't. Let's think about this like a massive manufacturing plant. The nucleus is the front office. The sperm shows up with the blueprint for a new product, and the front office is totally ready to receive it. But the cytoplasm, the actual factory floor, is a total disaster.
I really like that analogy. Cytoplasmic maturity is all about getting the factory floor organized. During maturation, organelles have to move to very specific locations. For example, tiny packets, called cortical granules, need to migrate all the way out to the inner edge of the cell membrane.
And those granules act like the security guards, right? They block other sperm from entering once the first one gets in.
Yes, that's the zone of reaction.
Yeah.
If the cytoplasm is immature, those security guards just haven't made it to the doors yet. Or consider a post-mature oocyte one that has been waiting around too long.
What happens to the factory floor if it's aging?
The machinery literally starts to dismantle itself. Those cortical granules actually migrate inward again, abandoning their posts at the membrane. The microtubule conveyor belts start to dissolve.
Wow.
So even if the sperm delivers a perfect blueprint and turns the lights on with calcium, the assembly line is physically rusted over, production halts, fertilization fails.
So what causes the factory floor to fall apart in the first place? Because the sources talk heavily about environmental sabotage happening while the oocyte is still growing inside the ovary.
Yeah, the follicular environment, which is the fluid sac surrounding the growing oocyte, it's intensely sensitive. The literature highlights severe underoxygenation as a major saboteur. If the dissolved oxygen in that follicular fluid drops below 3%, it dramatically increases the risk of meiotic spindle defects.
And the spindle is the delicate cellular machinery that pulls chromosomes apart, right?
Exactly, it's the mechanical rigging. If low oxygen damages that rigging, the chromosomes misalign. The oocyte completely loses its competence to fertilize properly.
And then there's oxidative stress, which came up a lot.
Oxidative stress is the ultimate cellular wrecking ball. Things like blood clots in the cumulus complex, the cloud of nourishing cells surrounding the oocyte, or systemic issues like maternal obesity, they can generate high levels of reactive oxygen species, or ROS.
Let's ground that concept. ROS are essentially highly unstable molecules that bounce around stealing electrons and just damaging cellular structures.
Yeah, they literally tear through the cell membrane and organelles. High ROS levels physically alter the texture of the oocyte's cytoplasm.
Really? Like you can see it?
Oh yeah, under the microscope, it can look dark, grainy, or pitted. The ROS damage the calcium storage tanks and the enzyme pathways. So going back to your analogy, the package arrives, but the recipient is too sick to even stand up and open the door.
Okay, so we have our two prime suspects. The sperm lacking the activation tools, or the oocyte lacking the cytoplasmic competence. This brings us to the final and arguably most important step of the interpretation mindset: action. What do we change next cycle?
All right, once the forensic unit identifies the suspect, how does the lab intervene?
Let's start with the most common intervention for a binding issue: the ICSI pivot.
So ICSI stands for intracytoplasmic sperm injection. In a conventional IVF cycle, you place thousands of sperm in a dish with oocyte and let them battle it out to chemically drill through the outer shell, the zona pellucida.
The natural way, basically.
Right. But if the issue is a binding defect, if the sperm is physically incapable of attaching to that shell, which happens in conditions like defective sperm zona pellucida binding types, unduly conventional IVF will give you 0 PN every single time.
So the immediate solution for the next cycle is to just bypass the shell entirely.
Exactly. With ICSI, the embryologist selects a single morphologically normal sperm, immobilizes it by basically tapping its tail, and uses a microscopic glass needle to inject it directly into the cytoplasm of the M2 oocyte. You completely remove the hurdle of penetration.
Okay, but we established earlier that simply putting the sperm inside the house doesn't mean the package gets open. What if you do ICSI, you bypass the shell, and you still get 0 PN? What if we're dealing with, like, a PLC zeta deficiency or globosospermia, where the sperm just doesn't have the match?
This is where the lab introduces the ultimate chemical workaround: AOA, artificial oocyte activation.
This sounds straight out of science fiction. How does AOA actually work?
It is brilliant cellular engineering. If the sperm cannot provide the spark, the lab provides it artificially. They use specialized chemicals called calcium ionophores.
Right, the sources mentioned a few of these.
Yeah, the most common ones mentioned in your sources are calcimicin, A23187, or ionomycin.
So they literally bathe the injected oocyte in a chemical solution.
They do. After injecting the sperm via ICSI, they expose the oocyte to this ionophore bath. An ionophore is just a molecule that can transport ions across the cell membrane, so the chemical literally forces open the membrane channels of the oocyte, allowing a massive influx of extracellular calcium from the culture medium to rush into the cell.
Wow, so it's mimicking exactly what the PLC zeta scissors were supposed to do. It kickstarts the calcium waves from the outside in.
Exactly. It forcefully wakes the oocyte up. The literature also mentions alternative methods, like using strontium chloride baths, which sensitize the calcium channels, or even electrostimulation, where they apply a microscopic electrical pulse to physically shock the cell into activation.
I have a major question here. If this calcium bath or this electrical pulse is basically a cheat code for life, if it bypasses the sperm's failure and forces the egg to activate, why don't clinics just use AOA on every single IVF cycle? Why not just use the cheat code from day one and guarantee it works?
It's a really tempting thought, but it highlights a critical point of caution in embryology. AOA is not a magic bullet.
Why not? If it forces the factory to turn on, doesn't that solve the problem?
Because forcing activation doesn't fix underlying genetic garbage. If the oocyte is genetically highly abnormal, or if the sperm's DNA is massively fragmented, AOA might force the cell to cleave and divide for a day or two. But that embryo is building from a completely shredded blueprint.
Oh, I see.
Yeah, it will almost certainly arrest in the dish or fail to implant later on.
Yeah. So you get a false positive of success, but no baby.
Exactly. And worse than that, messing with intracellular calcium is not something you do lightly. Calcium signaling regulates a massive downstream cascade of gene expression and embryogenesis. Unnecessarily flooding a totally healthy oocyte with a chemical calcium bath could theoretically disrupt the natural, delicate rhythm of development.
Ah, so you could ruin a perfectly good cycle.
Right. That's why professional guidelines strictly reserve AOA for forensic cases, patients who have demonstrated actual unexplained activation failure in previous cycles.
That makes total sense. It's a heavy intervention, not a daily vitamin.
Well said.
So let's bring this all back together for you, the listener. Facing a total fertilization failure at the 18-hour mark is gut-wrenching. It is the silent dish. But through the interpretation mindset, you can see that the lab acts as this microscopic forensic unit.
They trace the failure back to the source. They look at the sperm's activation tools. Is it missing PLC zeta or a function centriole? And they evaluate the oocyte's cytoplasmic machinery. Is it compromised by age, low oxygen, or oxidative stress?
And once they identify the culprit, they deploy highly targeted interventions, pivoting to ICSI to bypass a rigid shell or utilizing artificial oocyte activation to artificially kickstart the calcium waves when the spark is missing. It is biology functioning at the absolute bleeding edge of medicine, turning a cycle of heartbreak into actionable hope. But before we go, I want to leave you with one final mind-bending concept from our research stack today, something that totally flips the script on how we view the biology of reproduction.
Yeah, this is one of the most profound shifts in recent literature.
Throughout this whole deep dive, we've been forced to separate the male factor from the female factor, prime suspect 1 versus prime suspect 2. But recent studies show that an incredibly healthy, highly competent oocyte actually possesses the biological tools to repair fragmented, damaged DNA brought in by a defective sperm.
It is astonishing to think about. If a sperm delivers a highly damaged, shattered genetic payload, a strong, cytoplasmically mature oocyte can essentially act as an internal repair shell.
Which is just incredible.
It really is. It deploys its own enzymes to stitch the sperm's broken DNA back together before the first cell division even happens.
Think about the gravity of that for a second. What does this mean for patients? It means that early pregnancy loss, or even some cases of fertilization failure, might not just be a sperm problem because the sperm was damaged. It might be the exact moment the oocyte's internal repair shop finally ran out of tools and became overwhelmed by the damage.
It completely blurs the line between male and female infertility. We so desperately want to categorize the blame. But the reality is, the health of the oocyte dictates how much sperm damage can be tolerated, and the quality of the sperm dictates how hard the oocyte has to work. They are entirely interdependent.
Suddenly, looking for a clean, binary diagnosis, broken or not broken, feels like looking for a simple answer in a universe of complexity. The muddy waters of the embryology lab aren't just a place of clinical frustration, they're the exact place where the profound, intricate teamwork of biology is happening. And when one teammate falls short, the other steps up until they just can't anymore. We'll leave you to think about that.